You've seen the photo, the orange ring, the black center. Every science article used it. Every documentary opened with it. You think you know what a black hole looks like. But the real answer is much stranger than that. That photo isn't a photo of a black hole. It's a photo of light that got too close and never came back the same way. What you're staring at isn't the object. It's the wound it leaves in space itself. Let's slow down. In 1915, a physicist named Albert Einstein published a set of equations that changed how humans understood gravity. Not as a force pulling objects together, as a curve. Mass bends the space around it, the way a bowling ball bends a stretched sheet. Light doesn't fall into that curve because something is pulling on it. It falls because the space it's traveling through is no longer straight. Einstein didn't believe black holes were real. He thought the math was too extreme to exist in nature. He was wrong. A few months later, a German physicist named Karl Schwarzschild solved Einstein's equations for a very specific case. A single point of mass, so dense, so compact, that space folds completely around it. Schwarzschild described a boundary, a line where the curve becomes so steep that nothing, not even light, can climb back out. We call that boundary the event horizon. Here's what most people get wrong. The event horizon isn't a wall. It's not a surface. There's nothing there to touch. It's just the last point where escape is mathematically possible. 1 inch past it, and every direction you can move points inward. Every direction. Try to picture that. Not a place you can't leave. A place where leaving no longer exists as a concept. For decades, this stayed theoretical. A strange answer inside beautiful equations. Something scientists debated in chalk on blackboards. Nobody had proof something like this could form in the real universe. Then, in 1965, a mathematician named Roger Penrose did something no one expected. He proved, using pure geometry, that black holes weren't just a mathematical curiosity. If enough mass collapses in on itself, a black hole isn't just possible, it's inevitable. Penrose received the Nobel Prize in Physics for that proof in 2020, 55 years after he first wrote it down. So black holes were real, but nobody had seen one. You can't see something that traps light. There's no light bouncing off it to reach your eyes. So how do you photograph the unphotographable? You don't photograph the black hole. You photograph what happens around it. Picture a black hole surrounded by gas and dust, spiraling inward, heating up from friction, glowing white-hot before it crosses the horizon. That glowing material is called an accretion disk. It's not the black hole. It's the black hole's neighborhood, lit up and screaming on its way in. And here's where it gets strange. Some of that light doesn't fall in. Some of it gets close enough to feel the curve, whips around the black hole, and escapes in a new direction. Sometimes it circles 2, 3, 4 times before breaking free. This creates something called a photon ring, a thin band of light that has literally orbited the black hole before reaching your eye. That black center in the photo isn't the black hole itself. It's the shadow the black hole casts against that glowing backdrop. Scientists call it the black hole's shadow, and it's actually about 2.5 times larger than the event horizon hiding inside it. You're not looking at the black hole. You're looking at the hole it tears in the light around it. But light bending around a black hole doesn't behave the way light bends anywhere else in your daily life. Think about a straw in a glass of water. It looks bent because light changes speed, moving from air into water. That's refraction. Ordinary, predictable. You learned it in a classroom with a pencil and a cup. Gravity does something different. It doesn't slow light down or speed it up. It bends the space the light is moving through. The light itself never turns. It travels in the straightest possible line the whole time. It's the line itself that curves. That distinction matters more than it sounds like it should, because it means nothing chooses to fall into a black hole. Nothing gets pulled by some invisible hand. Space near the horizon is warped so severely that every straight path, every possible direction of travel, leads inward. Falling in isn't a choice a photon makes. It's the only direction left. Now picture a black hole surrounded by gas and dust, spiraling inward, heating up from friction, glowing white-hot before it crosses the horizon. That glowing material is called an accretion disk. It's not the black hole. It's the black hole's neighborhood, lit up and screaming on its way in. And here's where it gets strange. Some of that light doesn't fall in. Some of it gets close enough to feel the curve, whips around the black hole, and escapes in a new direction. Sometimes it circles 2, 3, 4 times before breaking free. This creates something called a photon ring, a thin band of light that has literally orbited the black hole before reaching your eye. That black center in the photo isn't the black hole itself. It's the shadow the black hole casts against that glowing backdrop. Scientists call it the black hole's shadow, and it's actually about 2.5 times larger than the event horizon hiding inside it. You're not looking at the black hole. You're looking at the hole it tears in the light around it. Even the shape of that shadow tells you something. A black hole that isn't spinning casts a nearly perfect circle. A black hole that's spinning, dragging space around with it the way a spoon drags water in a cup, casts a shadow slightly flattened on one side. Scientists can look at that asymmetry and estimate how fast the black hole is turning without ever seeing the black hole itself. That's the entire method. Watch the bending, measure the distortion, reconstruct the invisible thing from the damage it does to everything around it. In 2019, a global team called the Event Horizon Telescope Project turned that theory into an image for the first time. They didn't use one telescope. They linked 8 radio telescopes across the planet, from Hawaii to Antarctica to Spain, and synchronized them to work as a single instrument the size of Earth. A young computer scientist named Katie Bouman helped build the algorithm that could stitch together the scattered data from all 8 sites into one coherent image. She was a graduate student at the time. The image took years to process and confirm. What emerged was a picture of the supermassive black hole at the center of a galaxy called M87, 55 million light-years away, 6.5 billion times the mass of the Sun. The orange ring you've seen. The first image of a black hole's shadow in human history. 3 years later, the same team released a second image. This one closer to home. Sagittarius A, the supermassive black hole sitting at the exact center of our own galaxy. 26,000 light-years from where you're sitting right now. You have been orbiting it your entire life. So has every star you've ever looked at in the night sky. How do we even know it's there if we can't see it directly? 2 astronomers, Andrea Ghez and Reinhard Genzel, spent almost 30 years tracking individual stars near the center of the Milky Way, watching them loop around something invisible at speeds that only made sense if that something was millions of times heavier than our sun, packed into a space smaller than our solar system. Nothing else fit the data. Nothing else could explain stars whipping around empty space that fast. Night after night, year after year, their teams pointed telescopes at the same tiny patch of sky and logged the position of a handful of stars. One of them, given the plain scientific name S2, completes a full orbit around that invisible point in about 16 years, at speeds that touch nearly 3% of the speed of light at its closest approach. Nobody saw the thing S2 was orbiting. They saw the orbit, and the orbit was proof enough. They won the Nobel Prize for that discovery in 2020, the same year as Penrose. So here's where the twist lands. Everything you've seen, every photo, every headline, every glowing ring, is not a picture of a black hole. It's a picture of the evidence a black hole leaves behind. The bent light, the trapped stars, the screaming glowing gas on its way to a boundary it can never cross back over. The black hole itself stays exactly what it's always been. Unseeable, unphotographable. A conclusion, not an object. And maybe that's not so different from you. Think about how much of what you understand about the people closest to you is actually direct. You don't see someone's thoughts. You don't see their fear, their love, their exhaustion. You see the bent light around it, a tone of voice that curves slightly off normal, a habit that orbits a wound you've never been shown directly, a silence that has a shape even though you can't hold it. You spend your whole life reading the shadow something casts and calling that understanding. Somebody you love goes quiet for a week, and you don't see the fear underneath it. You see the bend, the short answers, the extra hour of sleep, the way they stand a little farther from the doorway than usual. None of that is the feeling itself. It's the accretion disk around it, glowing just enough for you to notice something is there. You do this with entire versions of yourself too. The parts of you formed by things you don't remember. A reaction that feels instant and unexplainable until you notice it always curves the same way, around the same invisible point. You don't see the event. You see how everything since keeps bending around it. Astronomers do the same thing, with better instruments and worse odds. They never touch the thing. They never will. Not with this telescope, not with the next one, not in your lifetime or several lifetimes after it. They just get close enough to watch how everything around it bends. And from that bending, they build a picture true enough to change what an entire species believes is possible. That's not a small consolation prize for never seeing the real thing. That might be the only kind of seeing that was ever available to anyone. Not just to astronomers pointing telescopes at the center of a galaxy. To you, pointing your attention at the people and the moments and the versions of yourself that never fully show themselves directly either. You've seen the photo. You thought it was a picture of a black hole. It was actually a picture of everything a black hole is close enough to change.